Yeah, so I forgot to record the morning class, so this will be the recording for both sections. All right, so any questions like PA2 or anything else? All right, well, let's continue what we started talking about yesterday, which was working with trees. And so we're going to construct a tree class by ourselves and use that on top of a node class. And let's just see how this works. So tomorrow I'm planning to introduce programming assignment 3. Okay, and I'll post that later on today. We'll talk about it tomorrow. We'll go through the details of it. It's going to involve a type of binary tree called a decision tree. So we'll talk in detail about what that means. We'll go through the specifications and requirements and so on, and see what this is about. But let's build just a plain old binary search tree today. So I'm going to start off with a node class. So I'll just call it node. And I will post this code on Canvas after class. So this is an integer node of a binary search tree. And as we mentioned yesterday, when we want to construct a node, usually it's because we have a data value that we want to store in the node. So we are going to make a constructor for this class. Constructors are optional, right? There's always a default constructor that just gives you an object, doesn't do anything else. It just handles basically the malloc and such. So what do we have in a node? We have a left child. We have a piece of data which I'm going to set up as an int, and we have a right child, and the left and right children are also nodes. Okay, so node contains two nodes. And then let's go ahead and make our constructor. So we can construct by specifying a data value. So our constructor, we use the keyword public, right? Constructors have to be accessible. And then instead of specifying a return type, we go directly to the name of what looks like a method, but it's the name of the class, node. Okay, this is going to be a constructor. And we're going to construct with a single integer, which I'll just call value. And my constructor will basically take the value that you pass to it and store that in the data field of this node. And then just to be clear, we'll set the left and right nodes equal to null. So it's a single node with no children. And that's all our constructor has to do. Alright, so let's write a traverse method. We don't have any data in our tree yet, but let's write a traverse method. So here's an Inorder Traversal. Public traverse is not going to return anything. So it'll just be a method called traverse. It doesn't need any arguments because we're going to traverse the tree whose root is this node itself. Right? So we got to think in terms of objects. We have an object of type node. When we call its traverse method, we're saying let's traverse the tree whose root is that object. So traverse the tree whose root is us, right? There's not really good language for that I found. Okay, well, how do we do this? We want to traverse the left subtree and then print out the root data and then traverse the right subtree. The left subtree is something we can get to just with the field left, right? But if left is null, we don't really want to try to traverse it, right? So here's what we want to do, left.traverse. And then print our data, and then right traverse. Okay, but the problem is, you know, if left is null, which is a legal value, then this is going to throw an exception. Okay, so we have to check this ourselves. So if left is not null, let's call left traverse. And if right is not null, then let's call right traverse. And in between, we'll print out the data. That's the in order part. Now, if you wanted to do pre-order, we would do our print before we do the two traversals. If we want post-order, we would move our print after both traversals. Okay, but the gist of it is basically the same. All right, so it's still a 3-line traversal function. All right, so let's make an add method. And remember, we have a tree. It's got, you know, potentially a bunch of nodes. And let's say this is, you know, whatever node we happen to be on. We can think of it as the root of a tree. If we want to insert something into this tree, what do? We compare the number we're inserting to the value at the root. And if it's bigger than that, we are going to insert somewhere into this tree on the right. And if the value we're inserting is smaller than the root, we're going to insert somewhere into this tree on the left. So non-recursively, right, we can start here, we can move left or right by comparing to the root. The recursive solution is easier. Basically decide which subtree you're going to insert into, and then call that root node's insert method. Alright, so what does this look like? So let's insert into the tree in sorted order. So this is not going to have to return anything. Let me just call it insert. Let's pass an integer, which I'll call value. All right, well, we have to compare the value we're inserting to the value of ourselves, right? We are the root node. So we want to compare our value to data. So if the value we're inserting is smaller than our data value, we want to insert into the left subtree. Which means do this. Sorry, value. Let me call this new value so we don't get it confused. So if our new value is smaller than the root node's data, then use the left subtree's insert method to add a new node containing that value. In other words, just punt, defer the task of actually doing the insert to the left subtree. Alright, so the possible complication here is if there is no left subtree, then this is going to throw a null exception, right? Well, if we're sitting at a node and we want to insert into the left subtree and there is nothing on the left, what do? Make a new node and set left equal to that new node. Okay, it's an edge case. So what does this look like? If left is not null, let's call the left subtree's insert method. Else, let's set left equal to a new node comprised of whatever the new value is. So there's our insert into the left side of the tree. Two possibilities. If we have a left child, let's just let the left child do the work. Say, hey, left child, insert this value into yourself, right? And we're good to go. But if we don't have a left child, we have to actually do the work. So construct a new node with the new value that we've been asked to insert, and just set our left child equal to that new node. Otherwise, just assume we should insert to the right. So, if our right child is not null, then call the right child's insert method. Otherwise, set the right child equal to a new node. So there's a working class for now. So this should seem fairly elegant, right? There's no explicit looping here. There's not a whole lot of weirdness, right? It's really just one edge case, which is if we don't have a child, make a new node. We don't have to return anything from here. We don't have to do anything with the return value the way we did in 222. Remember in 222, we did things like, you know, struct node star root, and then we always had to say root equals insert root comma 5, and so on. Right? And we had to do that because if root was empty to begin with, we needed insert to pass back the new root, which we would assign to root. But if root already existed, then this would simply return the original root, and this, you know, assigns root to itself. We don't have to do any of that in here, right? So our insert method just adjusts its fields accordingly, right? Changes something on the left or the right, or in a subtree of the left or the right. So let's see how we're doing syntax-wise. Pretty good. All right, let's write some main code. And I'm not going to work with a tree class yet. I'm just going to work directly with the nodes, okay? And then we will pass to the tree class separately, and we'll see what the issues are there. So let me just say node root equals new node, and we'll put a value of 50 in there. And let's insert some values. So we'll do a 23, we'll do a negative 200, we'll do a 0, we'll do a 15, we'll do a 16, we'll do a 14, we'll do a 144, and we'll do a 500. Alright, so we're just throwing some values into our tree. We're just writing test code here. And then let's call the traverse method. And if this works correctly, we should get our data values out in increasing order. 2 for 2, pretty good. You ready to try it? Let's run main. There we go. There's our nodes in increasing order. Our insert and traverse must be working. By the way, if you reverse these, right, to get your data in decreasing order. So we usually talk about left node right, and that's giving you the data in the same order that we're using in the insert method, right, smallest to largest. But if we do right node left, right, which just reverses the these two recursive calls, right, we get our data in decreasing order. So that's a freebie. All right. So is there anything wrong with this? Well, yeah. The problem with this is this first call here. When we say node root equals new node 50, we can't construct a node without specifying the value that we want, right? We could construct an empty node, but you know, when we're creating a tree, we don't necessarily have a data value in mind yet. We might want to read numbers from the user from a file and start putting them into a tree, right? And we would need to wire our code so that the first time we read a number, we say new root equals new node, or node root equals new node, that number. And then every time after that, when we read a number, we say, you know, root.insert. And that's a little awkward. It's more awkward with deletions, because now if we start deleting values, we need to somehow keep track of whether we've deleted the last value. Because when we delete the last value from a tree, root becomes null. And after that, if we say root.insert, we'll get an exception. So anytime we want to insert something into our tree, we have to know if this node that we call root is null or not. If it's null, we have to do this. If it's not null, we have to do that. And that's a really quirky requirement to put on the user. So we're going to wrap this node class in a class called tree. And tree is going to take care of that for us. Okay, it's going to decide what to do based on whether or not the tree is empty. Yeah, you can set pretty much any variable you want to null, right? Any type of object can be null, which is really useful. I don't think you can do this, right? But an integer you can. So small int, small float, those are primitives, but any objects, yeah, you can set to null, as far as I know. Okay, let's make a tree class. Alright, so our tree, we gotta have a root, and our root's going to be a node. And let's just initialize it, not a rot, a root. And let's just initialize it to null to say we have an empty tree. Okay, no nodes. Alright, let's make our insert method. So if the root is null, then we need to make a first node for our tree. Let's just set root equal to new node and construct a node with that value. So if the tree is initially empty, make a new node, set root equal to that. Now root is a tree that has a single node, and we can just return. Otherwise, the tree is not empty. It has a root. So let's use the root's insert method to do the heavy lifting for us. So we'll say root.insert value. That's all we got to do. Okay, left node, right traversal. So public void traverse doesn't take any arguments. So if the root is null, then we can just return. Otherwise, the root's not null, use the root's traverse method. So there's our whole tree class. So that still compiles. Let's go back to our main program and let's make root a tree. And this time, instead of, having to specify a value, we're just going to make root a new tree. And now we can start calling the insert method. And so there you go, there's your data values from the traversal. All right, making sense hopefully? Alright, let's add a height method. Alright, so height doesn't take any arguments, we'll just return the height of this tree. We have an edge case. We know that if the tree is empty, the height should be -1, right? But we're in the node class right now, right? So if we say something like node temp, and we've given it a value somewhere, and we say temp dot height, right? Since temp is a node, we can't be talking about an empty tree, right? There's a node here because we're using that node to access the height method, right? There's no way that this thing can be null. If it was, we couldn't have gotten to any of its methods. So we don't have to worry about the edge case where a tree is null here, but there is another edge case which is where this tree has no children. So remember the usual height algorithm. So height equals 1 plus the maximum of the height of the left subtree and the height of the right subtree. And we're going to find the height of these subtrees by using the height method inside those subtrees. So we're going to say left.height, right.height. But again, if left is null, we can't say left.height. We'll get an exception. So we have to deal with the possibilities that the left and right children are null. So if left is null and right is null, all we have is a single root. And what is the height of a tree with just a single root? Pop quiz. You can talk or you can chat. Awesome. Yes, it is 0. Thank you. Node with a single height, with a single node, is by def. Okay, so height is the number of hops from the root to the deepest node. So a tree like this has height 1. A tree like this, the distance from the root to the deepest node, well, there's only one node, the root, and the distance from the root to the root is 0. So that's a height of 0. And then the null tree, we just use by definition, the height is -1. So yeah, this is counterintuitive, right? One node looks like a height of 1, it's actually 0. We go down by 1. Alright, so if left and right trees are null, then we return a 0. Okay, if the left subtree is null, okay, if we get past that, then we know that we don't have just a single root. So if the left subtree is null, then our tree must look something like this, right? It has stuff on the right. We know the right is not null also, because if left is null, right, well, if right was null also, we would have already exited. So if left is null, then we know the right subtree is not null, so we can use right's height method. So we'll call the height method on the right subtree. We will add 1 to that, right, because it's always 1 plus, well, we don't have a left subtree, so it's just 1 plus the height of the right subtree. So return 1 plus right height. On the other hand, if right is equal to null, then the left subtree is not null, so we can use the left subtree's height method. So return 1 plus left dot height. So in the general case, we have 2 subtrees to consider. So we'll just call the height methods on the left and right subtrees. So if the left tree is taller, we'll return 1 plus the left subtree's height. Otherwise, the right tree is taller or equal to the height of the left, and so we just return 1 plus the right subtree. And that should be our whole height function. Alright, well, let's make this so we can call the height of a tree instead of the height of a node. So we'll go back into our tree class. Right, and we'll just return the height of the root node. With one possible detail, which is the root starts off null. So if we have not added anything to the tree, or if we've deleted everything we've added, this will throw an exception. So we handle our edge case. Where the root's null, we just return a -1, so we hardwire that. Alright, so into our main class. Alright, so we'll call the height method and print out the height. I'll put some space in the beginning there. Compile that, run it, and there's our tree, and it says our tree has a height of 4. Alright, let's double check. Let's make sure that's what it should be. So we are inserting 23, negative 200, 0, 15, 16, 14, 144, and 500. Alright, so 23 will be the root. Negative 200 will go to the left. 0 will go to the left of 23, to the right of negative 200. 15 will come to the left, will go to the right, will go to the right. 16 will go to the right of 15. 14 will go to the left of 15. 144 will come over here, and 500 will come over here. So the deepest nodes are down here. The number of hops, 1, 2, 3, 4. So that tree has a height of 4. So at least for this case, our height function does seem to be working. So any questions about this, right? This is really just kind of demonstration, but you know, it's 222 stuff in a more kind of a cleaner approach. All right. Well, let's continue. So let's rebuild our classes, but let's make a tree of strings. So when I say, right, this is going to be a string node of a, I don't even know what that comment means. So when I define my node, right, left and right children are still going to be nodes, but my data is going to be a string instead of an int. Okay, so I have to change that. When I construct and I pass a value, that value I pass has to be a string instead of an int. When I insert, the value that I insert has to be a string instead of an int. And the height is still going to, right, it doesn't take any arguments, so that's not going to be affected. So I've changed 3 places where I said int to say string. Okay. There's one other thing that I need to change though, which is in here where I say if the value I'm inserting, the string, is less than the data value. Well, we can't use less than for strings. Okay, we have to use this compare to method. So I'm going to say if compare to new value is less than 0. All right. So sorry, if data. Okay, so if the value we're inserting compared to data is less than 0, okay? This means that this string, the new string we're inserting, comes before the root node's data, okay, alphabetically. So instead of new value less than data, we say if new value compared to data is less than 0. Okay, but that's all we had to change for the node class. Basically change the word int to the word string and then change that one comparison. Okay, if we go into the tree class, our insert method should be a string. Our height method doesn't change at all, and that's it, right? We had to change one reference in the definition of our insert function to say insert a string instead of an int. And that works now. Okay, now our main code is obviously going to have to change. Instead of inserting numbers, we're going to insert strings. Alright, so we're just going to insert some strings into our tree. Nothing about how we did this changed, except obviously we have to pass string values. So that still compiles, and when we run it, that was interesting. Oh, I'm in the wrong directory. Alright, so everything fine except for extra parenthesis in our node class. So let's just get rid of that. And let's go ahead and run our program, and there's our strings in order. And the tree height is still 4, obviously. So changing from one type of object to another, pretty straightforward, right? Okay, let's make a tree of rectangles. We got a few minutes. And I'm going to ignore this evil stuff. Alright, so here's our old rectangle class from week 1, right? It's got a height and a width. Let me make these ints, because they print nicer. So it's got a height and a width. It's got a couple of 3 different constructor methods. I don't know why I'm harping on doubles all of a sudden. So 3 constructor methods. It's got an area method that returns the area, perimeter method, some accessors, some mutators, and a toString method, which just prints out the height and a cross and the width. Okay, so there's a rectangle class. I'm getting tangled up. Alright, we're in the same place now. So let's look at our node class. And our strings are now going to be rectangles. And our comparison, well, let's just compare area. So if our value that we're inserting has an area which is less than this rectangle's area, then we'll insert to the left. So ordering of rectangles is ordering by their area. So that still compiles. Let's look at our tree class. That just changes one spot, which is where we declare the insert function. That still compiles. Let's look at our main. So we're going to construct a new tree, and let's insert a new rectangle, which is going to be 2 by 4. So let's make a bunch of rectangles. So we'll do a 3 by 5. We'll do a 5 by 7. We'll do a 1 by 1. We'll do a 0 by 2. It may not let us do a 0 by 2. We'll do a 1 by 2. We'll do a 9 by 8. We'll do a 8 by 10. And we'll do a 4 by 5. And we run this, and there's our sorted list of rectangles, right? We built a binary tree out of rectangles, and so when we traverse in order, left node right, they come out in increasing order of area. So 1, 2, 8, 15, 20, 35, 72, and 80. And so the thing I want you to think about from this is how little has to change whether we're making a binary search tree of integers or strings or rectangles or hash maps or indexers or anything else that we decide, right? Other than this business of comparing, which, you know, for integers, for strings, and for rectangles are different. Other than that, it's really just replacing the word rectangle with indexer or even, right? If we want a tree of even elements and so on. And so we can define what's called a generic. We've used these with linked lists and hash maps. That thing that you put in the angle bracket, well, we can define our class, right, and say this is a generic class. And down here we can say T, and when we construct, if we say node angle bracket integer, it'll say integer data. And down here, when we say insert, instead of rectangle new value, we can say T new value, and it would replace it with integer new value. Okay, so generics will let us write things like linked list and hash map that work with different types of data. There's a few complications, in particular this comparison business, so we'll work through that tomorrow. And then we'll mostly go over PA3 tomorrow, and then I'll talk about a few more things. I've posted the quizzes on Canvas. I opened those up. They're due in a few weeks. So we'll take a look at those and ask questions. Okay, there's some details on try-catch blocks and so on. And we have to talk about statics more carefully. All right, there you go. Binary search trees in Java. Have a great afternoon. I will catch you tomorrow.